So we know pressure is 101,325 pascals at sea level. But as you go above or below sea level, pressure changes. That's why you might experience your ears popping when you go below the surface of the water and you're swimming, or you're up high in an airplane. So specifically, as altitude increases, pressure decreases. So as you go up to the top of a mountain, there's less air pressure up there. However, that pressure change does not happen linearly, and it's not something that's easy for us to study. So this statement is not part of the AP curriculum. However, this next statement is, as depth increases, pressure increases. So we can see here that we have this scuba diver guy who is below the surface of the water, and because his depth is increasing, the pressure acting on him is increasing. So if pressure increases with depth, we can calculate the change in pressure with the equation P equals rho GH. This P technically is gauge pressure, because gauge pressure is defined as the change in pressure from sea level. And rho is the density of the fluid, G is the acceleration due to gravity, or 9.8, and H is going to be the height of the fluid, or the depth that that person is at. Another statement that's helpful to know is that the absolute pressure acting at any point is equal to the sum of all of the fluid pressures above that point. So looking at this conceptual example here, we have some fish that are swimming underwater. And let's look at this fish right here. So if I wanted to know the absolute pressure on him, let's turn him into a dot. Let's draw a line above him. So the absolute pressure acting on this fish would be the pressure change due to the water, to the depth of the water, plus 101,325, the air pressure that's above him. I just have to add all of those pressures together. So let's look at a couple of examples. In example 1, it says a container is completely filled with water and then sealed. What is the absolute pressure at point 2, which is 25 centimeters below the lid? So when you draw a picture and we have an equation that has an H in it, we need to define where H equals 0 is. H equals 0 doesn't have to be the ground. In this unit, it's going to be helpful to make H equals 0 to be sea level. That's going to be the location where atmospheric pressure is 101,325. So I'm going to make the lid of the container H equals 0. So the pressure here is 101,325. And we're down here at point 2. So I know that pressure increases with depth. And as I go deeper into the water, the pressure is going to increase. And to calculate that, there's a couple of ways that I can do that. The first is to use the gauge pressure equation. So the absolute pressure is actually going to be equal to the gauge pressure in this case, because there's nothing else above point 2 except for the water. There is no air because there's no air in the container, and that there's a lid on the container, so the air pressure above the lid isn't affecting point 2. So the gauge pressure at point 2 is equal to the absolute pressure. So that would be rho GH. Rho is 1,000, the density of the water, times 9.8 times my depth, or the height of the water above me. So 25 centimeters converted into meters, and the absolute pressure at point 2 is 2,450 pascals. Another way to look at it is to look at the equation involving all of the vocab and kind of talking to myself. So the absolute pressure is equal to the atmospheric pressure plus the gauge pressure. Well, there is no atmospheric pressure because there's a lid on the container, so that's 0. So all I have left is the gauge pressure. So just two ways of looking at the same thing. Let's look at a second example. In example 2, It says the container is then opened. What is the new absolute pressure at point 2? So in this case, at point 2, the absolute pressure at point 2 is equal to the sum of the pressures of everything that is above me. So I have the water above me and I have air above me because the container is now open. So again, I can use the same equation. This time I do have to add in the atmospheric pressure of 101,325 plus the gauge pressure, and you can see that the pressure has increased a lot in the open container. Next, let's look at this more complicated example. It says a student fills a graduated cylinder with 15 centimeters of honey, 18 centimeters of water, and 20 centimeters of vegetable oil. The layers separate by density. The student then drops a popcorn kernel into the cylinder and it comes to rest on the water-honey interface. So this is the popcorn kernel. What is the absolute pressure acting on the kernel? So the absolute pressure is going to be equal to whatever is above the kernel. And that is going to be water, oil, and air. So again, the honey doesn't come into play. So next, we can calculate that by knowing the height of each of those layers. So water is going to be rho GH, oil, rho GH, and then our air pressure, 101,325. So plugging in our numbers, the density of water is 1,000 times 9.8 times the height of the water. And the height over here is 18 centimeters, so 0.18 meters. The density of oil is 910 times 9.8, and the oil is 20 centimeters, or 0.2. And then the air pressure, which is atmospheric pressure, 101,325, and the absolute pressure acting on the popcorn kernel is 104,873 pascals. Let's look at 3 common conceptual questions. Question 1. Why are the bubbles near the snorkeler smaller in diameter than those near the boat? So we have an image over here, this guy snorkeling, and you can see the bubbles coming out of his snorkel are smaller by the snorkeler, and then they are larger by the boat. So pause the video and discuss this with your neighbor, and then I'll click to reveal the answer. So yes, because the pressure is greater near the snorkeler, there's more force acting on the air bubbles, compressing them, so they are going to be smaller than the air bubbles near the boat. All right, question 2. 3 holes are poked in a 2-liter bottle of water. Why are the paths of the exiting streams of water different? Pause the video and talk to your neighbor. Yes, because the pressure of the water is greater at point C, the water is going to exit the bottle with a greater horizontal velocity. And if it has a greater horizontal velocity at point C, it means it's going to have a greater horizontal distance. And lastly, question 3. The following apparatus is filled with water. At which point A, B, C, D, or E is the pressure the greatest? Again, pause the video and talk with your neighbor. Did you get it right? It's a trick question. The pressure at all points is the same. Pressure does not depend on the volume of water above the point. It depends only on the height of water above the point. And as you can see, the height in all 5 different columns is the same. Therefore, the pressure is the same at all points.